here it is. This is the last lesson I will be doing for Physics 12 this semester, unfortunately. Here we go. So we're going to look at parallel plate energy kinds of problems, and these things could get a little bit involved. Here we go. So for parallel plates, the voltage is merely given by the batteries. The way these things are set up is, some of you have seen circuit stuff, some of you hadn't, but this is a simple circuit. These represent wires. This thing represents the battery, where one end is 0 and the other end is the voltage of the battery. We can recall that for a test charge placed at a point whose voltage is known, we can find the potential energy using the following. PE equals Q times V. We've also seen that work is equal to the change in potential energy, which is equal to the charge times the change in voltage. V stands for voltage in these, or big V stands for voltage in this particular context. So we want to find the work done by an external agent that moves a positive 2.5 microcoulomb charge from the negative plate or the grounded plate to the positive plate, and we're told that the positive plate's at 120 volts. And we can assume in this particular case that the charge begins and ends at rest. Well, if that's true, this is relatively easy. It's an energy problem. Energy initial plus work equals energy final. Initially, there is, well, we can say there's potential energy initial plus work equals potential energy final. We're told it begins and ends at rest, so no kinetic energy. But if we look here, I'll just fill it in, never mind, 1 sec. QVI plus work equals QV final. Initial voltage is 0, so that's gone. So my work is just going to be equal to the charge times the final voltage. In this case, that's going to be, we are told, 2.5 times 10 to the negative 6 times 120 is 3 times 10 to the negative 4 joules of work. It would take that much work to move this positive charge to this positive voltage, and we'd have to, we're putting work into the system because these things are naturally going to repel each other. If we did something like this, I'm going to find the final speed of an electron beam if it is accelerated by 125 volts. So we can work this the other way. There's actually some interesting applications of this. Let's say we have an electron, and we have this thing down charge, or down, I don't know what the word is, but we've got this thing set at negative 125 volts, and this thing's grounded up here at 0. So we can see a few things here. We cannot use forces. Cannot use forces because the only thing we have here for that is F equals QE, and E equal, or F, the force, electric force equals QE, and E equals the change in voltage over the distance, and we don't have the distance. We don't know what this is. So we have to find the speed of this electron a different way. The way we have to do that is, because we can't use forces, we have to use energy. Just like before, there was some questions that we could use energy and kinematics for, depending on what information we were given. We can't use kinematics or dynamics here because we don't know what the force is, so we can't, because we don't know the electric field, because we don't know the distance, so we can't find the acceleration. So we've got to use energy. Energy initial plus work equals energy final. At the beginning, all we had was PE plus work equals, at this end we have kinetic energy. There's no external agent, so system energy is conserved. If system energy is conserved, there's no work done. So QV, and there's no potential energy here because the voltage at this point is 0 at the end. So QV is going to equal 1/2 mv squared. It's important for you to recognize that this v is velocity and this v is voltage. There is no way around having to use both those letters. So we've got a charge of negative. Remember, we use the charge sign on and with an energy question. Negative 1.6 times 10 to the negative 19 is my charge. My voltage is negative 125 volts, and it's going to equal 1/2 The mass of an electron is 9.11 times 10 to the negative 31 VF squared, and that VF is the final velocity. If we actually run those numbers, I'll let you do the calculation. V final equals 6626295.62 meters per second. So that's 6,626,295 meters per second. That electron is moving incredibly fast. We see from the above calculations actually a really neat result here. This line is quite a neat result. So I'm just going to collect it here. QV, I'll make that obviously bigger, hope, equals 1/2 m little v squared, where it's important to remember this guy here is voltage, and this guy here is velocity. M is obviously the mass. Yeah, and away we go. So let's keep doing a couple more examples. I think there are, hold on, how many are there? There's just three more after, there's three more. So example 3. An electron already moving at 5 times 10 to the 5 meters per second enters a set of accelerating plates. It goes from, there's a 100 volts and a 600 volts, and we want to figure out how fast this thing moves when it leaves the plates. Now, we've got the distance here, so we could actually find E. If we use the distance, we could find E. We can use E to find the force. We use the force to find the acceleration. We can use kinematics, but I'm not gonna. I'm gonna use energy. We could use kinematics if you felt so inclined, but I'm not going to. I want to show you how energy works in this particular case. So we've got energy initial plus work equals energy final. There is no outside agent here, so the work done is 0. So my energy initial is the kinetic energy, and that's going to equal my KE final plus my potential energy final. Actually, we've got potential energy initially as well, because there's going to be potential energy here at the 100 volt plate, and there's going to be potential energy here at the 600 volt plate. Neither of these are 0, so there is going to be some potential energy to end this thing. So let's see how the numbers here play out. We've got PE equals Q voltage initial plus 1/2 mv squared is going to equal, or mv initial squared is going to equal 1/2 m velocity final squared plus Q voltage final. I'm not going to put in any values here. I'm just going to move some stuff around, and I'm going to show you how this is going to end up. I'm going to start bringing everything over. So I'm going to subtract this QV final over. So we're going to have QVI minus QVF plus 1/2 MV initial squared equals 1/2 MV final squared. And now I'm going to start putting some numbers in here, and I want to show you an interesting thing that happens. So we're going to have Q is, it's an electron, we're told right there. See, look, electron, negative 1.6 times 10 to the negative 19 times 100 minus negative 1.6 times 10 to the negative 19 times 600 plus 1/2 m, nope, 1/2, we know the mass, 9.11 times 10 to the negative 31. And we know that this thing is traveling at 5 times 10 to the 5 squared equals 1/2 9.11 times 10 to the negative 31 V final squared. The thing I want to show you is actually has to do with these two terms here. So you can see that we've got a minus minus here, which means what we're going to actually end up having is we're going to have this term minus this term. So I want to write that out here, and I'm actually going to factor out this charge here. So we're going to have, no, I'm not. I'm going to write it like this. We're going to have 1.6 times 10 to the negative 19, because minus minus is equal to a plus, times 600 minus, and I'm going to pull this minus out. It's mathematically equivalent. 1.6 times 10 to the negative 19 times 100 plus, and I'm just going to go like this. Dot, 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 and bring this whole thing down, because the thing I want you to see is right here. What we get here is that we're actually going to end up, and now I could factor out this, and we could see here that I would get 1.6 times 10 to the negative 19, and then we get 600 minus 100. Well, this is just going to be 500 volts. If you think back to when we were doing relative velocities in kinematics with those trains moving in relative to each other, we can kind of imply or use that, that same logic here. Instead of using 100 volts and 600 volts, what I could have done is I could have just said, because all we care about is the difference in the voltage between the plates, what I could have done is I could have just subtracted 100 from both of these, making this 0 and making this 500, and I wouldn't have had a potential energy term there. I'm allowed to do this because we see if we don't do it, we just play through all the math, all we care about is the difference in the voltages anyway. So all this work to show you that all we do actually care about is that delta V is 500 here, and so I could have used that as my final voltage anyway. The difference between the voltages, I could have made this one 0 and I could have made this one 500. At the end of all of this, let's just do this. I want to mark this in green. The end result of this calculation right here is that the final velocity, VF, is equal to 1.33 times 10 to the 7 meters per second, and I'll let you verify that. So this electron has been sped up, which makes sense. It is negatively charged, and we've got a positive voltage here, so of course it's going to accelerate towards it in this area. And so that makes sense. Where it gets interesting is when we do something like this, where we've got a 0 voltage here, we've got some voltage here, and then we send this thing through plates. Well, because what's going to happen here? As we've seen between these two plates, there's going to be an electric field downwards. And what happens is this thing is going to be accelerated. It's going to have some final velocity, and then it's going to enter this area here. Well, this is an electron. We can see because we're told this is minus. Well, maybe it's not an electron, but it's a negatively charged object. Well, actually, the question says it's an electron, so it's an electron. What's going to end up happening here is once it enters these deflecting plates, there's going to be a force upwards on it. This is a positive plate. This guy's going to be attracted this way. There's going to be a force up. And so what that's going to do is as this electron is flying through here, it's going to start to deflect upward. It's going to bend upwards. It's going to be moving so fast that it probably won't actually hit these plates depending on what the strength of the electric field is. And the important thing to recognize is that we can actually start to manipulate this voltage here to make the electric field stronger or weaker. If we make it stronger, well, the electron will bend harder and go up higher over here. If we make it weaker, or make it even 0, we could theoretically send the electron straight through. We could switch the polarity. And make the electron go the other way. We could make this positive and this negative. And so what we get here is actually, this is the precursor to the old kind of deeper TVs, the CRT TVs. Actually, I have 2 of these kinds of TVs in my classroom, the ones that you may have seen underneath the windows over there. This is the rough technology behind how those things work. There's actually, it gets a little bit more complicated than that, and if we had talked about magnetism, we would have seen that. But this is the basic idea, where you've got these electrons flying towards a fluorescent screen that lights up when the electrons hit it, and we can choose where the electron goes by manipulating the voltages in these two plates, because we're creating an electric field and the thing goes up or down. And in the case of a television, we'd have ones on either side, and so we'd have this thing going up, down, left, and right, and we could choose exactly where on the screen got illuminated, and that's how we would get a picture. It's really quite a neat application of this kind of technology. So there's one more example that we're going to do here involving exactly that kind of thing. So we've got this set up. We've got an electron being accelerated between two plates. The difference between them is 1200 volts. It's going to enter this area here. We can already see that there's an electric field going downwards here. And so as the electron enters it, it's going to start to encounter a force. It's going to deflect up, and we want to know, it's going to follow this path here. And it's going to start to deflect up. What we want to know, if there had been no electric field, it would have gone straight through. What we want to find is the vertical displacement of the beam when it leaves the CRT, or the cathode ray tube. And so what we want is actually this displacement right here, because actually what would happen is this would be a straight line after it leaves the television, or after it leaves this part of the tube. And so this is the distance we want here. I'm going to call that D for displacement. That's what we want. So let's take a look at this. The first thing we need to do, and I'll just talk us through it first. The first thing we have to do is we have to find V final at this point. And to do that, we're going to use energy. We don't know the distance between these two plates, so we don't know, and we can't figure out the electric field strength there, so we're going to use that. The next thing we're going to end up doing is we're going to look at, this question kind of outlines it, find the speed of the electron after it leaves the electron gun. We want to find the vertical acceleration of the beam in the deflecting plates. So at this point here, it's going to start to experience a force up, which means it's going to start to receive an acceleration up, and we want to find out what that is. Then we want to figure out how long it takes to go from here to here, because that'll tell us how long it's been accelerating for. And then we can find the angle and speed at which it leaves the CRT, and then we can find the vertical displacement. There's a lot going on, but let's go. So let's go over here, part A, energy. We can find out how fast this thing's moving, because we've got that interesting result that the potential energy initial equals the kinetic energy final. So we've got QV equals 1/2 m little v squared. So we've got negative 1.6 times 10 to the negative 19 times the 1200 volts equals 1/2 the mass of the electron, 9.11 times 10 to the negative 31 v final squared. You do that math, we find out that the speed of the electron as it leaves these plates is 20,530,826 meters per second. Okay, well, let's go. Part B. I will do part B below. I still want to leave that picture there, so let's do part B. We want to find the acceleration in the y direction throughout the time that the electron's in this zone. So we've got, I'll write it all out, we've got F net equals ma. We know that F, the only force acting on this electron, we can ignore gravity because the mass of an electron in this case is so small. So we've got F equals QE. We could include it, but it would do nothing. We've got E equals delta V over D. And so if we plug all of these things together, what we're going to see is that Q delta V over D equals ma. So then a y is going to equal Q delta V over md. and I can start to fill in these values. Q is 1.6 times 10 to the negative 19. This Q came from this force, and remember, when we're dealing with forces, we don't include the positive and negative on the charge. All we care about is the direction of the acceleration of the force, which we've already found is going to be up, because this thing's negative and that's positive. The change, or the voltage difference, we're told right there is 750. The mass of the electrons in the electron beam is 9.11 times 10 to the negative 31. And the distance here is 2 centimeters. So 0.02 meters. What you find out is that the acceleration is 6.6 times 10 to the 15 meters per second squared. Well, the next piece we need to know is how long is the electron beam undergoing that acceleration? So we can take a look at it this way. Parts, I've already used red, let's use orange. Part C, here we go. All the information I need right there. We know that the acceleration horizontally equals 0. We know that the horizontal velocity is 20,530,826 meters per second squared there. We know that the distance the electron is traveling while it's in that area is 5 centimeters, so 0.05 meters. We want to find the time. This is a kinematics problem with constant acceleration of 0. So T equals D over V. So that equals 0.05 divided by 20,530,826. We find the time is 2.4 times 10 to the negative 9 seconds. It's not in there for very long. So let's look at this last piece here, or second last piece here, this part D. We want to know, or we want to find the angle and speed at which it leaves the CRT. So this thing is going to have components of velocity. It's going to have a horizontal component, which we already found to be 20,530,826 meters per second. That's not going to change. It won't. It can't. But we're adding a vertical component. So we have to figure out what that is. We know that initially VIY equals 0. We want to find V final Y. We know that the acceleration upwards is 6.6 times 10 to the 15 meters per second squared. And we know that the time it takes to make this acceleration is 2.4 times 10 to the 9, or negative 9 rather, seconds. So we can use this information to figure out what this Vy component is. We use this kinematic equation, V final equals V initial plus AT, and we find that, well, the final velocity is just going to be these two numbers multiplied together, and we find that V final Y is 1.58 times 10 to the 7 meters per second. So that's this guy here, 1.58 times 10 to the 7 meters per second. Now we have found the horizontal component. We know the horizontal component from part A. We found the vertical component here by figuring out how much velocity was added. And now we have to put this thing together to figure out the angle and speed at which this thing leaves the CRT. The vertical and horizontal are perpendicular to each other, so we can use trig to find the angle. If you use tangent to find the angle, you will find that this angle is 37.65 degrees. Tan inverse of opposite over adjacent. You know what? I can write that out. Tan inverse of 1.58 times 10 to the 7 divided by 20,530,826. And using Pythagoras, we can figure out this, the total velocity using this squared plus this squared, square rooted. I'll let you do that calculation if you want. This, I did it, and I'll tell you it's 25,900,000 meters per second. The last step is to find the vertical displacement of the beam when it leaves the CRT. That is just one additional piece here. So I want to put part E down here. We know VIY, we know VFY, we know A, we know T, we know V final, which we found right here in the Y direction. So to find the vertical displacement of the beam when it leaves the CRT, all we're looking to add now is here is dy equals question mark. We know the and this is actually the acceleration in the Y direction there. So I know the acceleration, I know the time, I know the initial velocity was 0. So this is actually really quite straightforward. dy equals VIYT plus 1/2 AYT squared. VIY is 0. So dy is going to equal half 6.6 times 10 to the 15 times 2.4 times 10 to the negative 9 squared. We can find that dy there is 0.019 meters, which is the same as 1.9 centimeters, is the vertical displacement of the beam as it leaves the CRT. That is everything using, well, basically everything that we've looked at except circular motion, which if we got to magnetism, we could add. But we, aren't gonna, so we can't. This is it for this chapter. I hope it's made some sense. I'll zoom this out a little bit so you can see the whole thing. As always, comments, questions, concerns, please fire me an email. The questions I want you to do for homework are as follows. I would like you to do 1 to 4. I would like you to do 6. I would like you to do actually 1 to 4 and 6 to and 6 to 10. There's some quite good questions in there. As always, as I said before, comments, questions, concerns, please fire me an email or come to my office hours.